Okay, I'm going to do a review for test 3 by going over an old test 3 of mine from fall of 2001, and this is on material from third semester calculus. So first we're going to calculate some double integrals. These should be fairly straightforward, but let's go ahead and look at them. For this one, we're just integrating first just the x here, and so x is a constant when we integrate with respect to y, and so we just get yx. And we want to evaluate this from y equals x to y equals x squared. So I'm going to have, for the y part, just x squared minus x. And of course, you can multiply that out, get x cubed minus x squared. And then when I integrate x cubed minus x squared, I get x to the fourth over 4 minus x cubed over 3. And then I evaluate this just by plugging in 1 and 0. 0 is just going to give me 0, but at 1, I'm going to have 1/4 minus a third, which will be minus 1/12. So the answer to this question was minus 1/12. Now notice that x is always positive. X is between 0 and 1. And we're integrating something positive and we ended up with a negative answer. So that might bother some of you. But let me point out that x squared is less than x when x is between 0 and 1. So for example, if x were a half, x squared would be 1/4. So x squared is smaller than x. So really, if you want to think of in terms of getting something positive here, we should be integrating from x squared to x, and that would be minus this. So this is going to be negative because the x squared is less than x. Part B was this double integral. And part of this is just testing to make sure you don't throw in an extra r when I don't give you an r there. So this you should just do directly like it's written. And we just evaluate this first by integrating dr. And it's really a 1 dr, so we end up with r when we integrate. R evaluated from 0 to 1, and that's going to give us 1. So we get the integral of 1 d theta, and that's going to be theta when we integrate. Theta evaluated from 0 to pi, and that's just going to give us pi. So that's the answer to part B of this question. The second question involves a piecewise function in two variables where the value of f depends on where you are in the plane here. So let me do part A first. We'll come back to B. So if I look, x is between 0 and 4 everywhere. And y is between 0 and 5, between 0 and 3 here and then up to 5 here. So let me put this picture here. We have x between 0 and 4 and y between 0 and 5. When x is between 0 and 4 and y is between 0 and 3, so that's down here, we're going to have part of the function being defined a certain way, namely as 2. And then for x between 0 and 2, so in here, with y between 3 and 5, we have the function defined as 1. And then this last part where x is between 2 and 4 and y is between 3 and 5, we have f defined as minus 3. So I'm going to go ahead and indicate this by putting a circle in here. 2 is the value of f in this rectangle. 1 is the value of f in this 2 by 2 square up here, and minus 3 is the value of f in this 2 by 2 square. So when I do this double integral of f dA, I'm really getting a volume in some sense, except for this part that's below the xy plane. So I get a volume here. It's a 3 by 4 by 2 box there, because the height's 2 inside this region. So that's going to be just 3 times 4 times 2. This is a 2 by 2 by 1 box, so this is going to be just 2 times 2 times 1. And here I'm going to have 2 times 2 times minus 3. It's because the negative 3 here, we were below the xy plane, 3 in that direction. And so this box will be 2 by 2 by 3, but it's below the xy plane, so we get a negative value for that. So again, we get 3 times 4 times 2 for the value of the double integral in this rectangle. And then we have 2 times 2 times 1 for the value inside this square. And then 2 times 2 times negative 3 for the value inside this square. And so that gives us 24, let's say minus 12, that gives us 12, and then plus another 4, that will be 16. So the answer to part A here is 16. Now part B is related to the same function. Make some room here, put part B right here. And we want to evaluate now this double integral. So x is just between 3 and 4, which was in this area right here, and y is between 1 and 5, so y is going from 1 to 5 here. So the only thing we're interested in is x between 3 and 4 and y between 1 and 5. Up here, we'll have f defined as minus 3, and here we'll have f defined as 2. Let me go ahead and change this picture to agree with that. So f is 2 here and minus 3 here. So here we have a 1 by 2 rectangle, and the height is 2. And here we have a 1 by 2, and again, the height's 3, but it's in a negative direction. It's below the xy plane. So we want to multiply 1 by 2 by negative 3 there, 1 by 2 here. So we have 1 times 2 times 2 plus 1 times 2 times negative 3, or 4 minus 6, which is negative 2. So for part B, the answer will be negative 2 to this question. Let's go to problem 3. Here, this is a region in the xy plane, but in polar coordinates. Now let's just make sure we understand the graph here. R equals 1 minus cosine of theta. When theta equals 0, we have 1 minus 1, r is 0. So when theta equals 0, that's a positive x-axis. R is 0, you're right here. And then when theta equals pi halves, you're up at the positive y-axis here. And when theta equals pi halves, this will be 0, so we'll just have 1. So we're at 1 on the positive y-axis. The negative x-axis is where theta is pi. And when theta equals pi, we see we have 1 minus a negative 1. So r will be 2. And at 3 pi halves, you can see we're going to be at 1. And then when we're back at 2 pi, back at where we started, we'll be at 0. So this is going from 0 to 2 pi, going all the way around for theta. So we want to integrate this from theta equals 0 to 2 pi. For r is just going from the origin then to the curve. So r is going to go from the origin to the curve for each fixed theta. And so for each fixed theta, we have r going from 0 to 1 minus cosine of theta. And don't forget, this is area, so the dA has to be replaced with r dr d theta. So again, theta is going from 0 to 2 pi, all the way around the origin here. And then r is going from 0 to 1 minus cosine of theta. And this is dA. So now we just want to evaluate that. The integral of r will be r squared over 2. We want to evaluate that from r equals 0 to 1 minus cosine of theta. Of course, at 0 we'll have 0, but we need to square the 1 minus cosine of theta. And I'll just go ahead and multiply that out, 1 minus cosine of theta squared, and it's over 2 again. So we're going to get the 1/2 coming from this 2. And then when I square this out, I get 1 minus 2 cosine of theta plus cosine squared theta. So I want to integrate each of these. Let me go ahead and rewrite cosine squared theta the way we usually do. That's 1 plus a cosine of 2 theta over 2. And now we have a number of things to integrate. But let me point out, when we integrate cosine of theta, that's going to be sine theta. And when you evaluate that at 2 pi or 0, sine theta is 0. So when I integrate this, I'm just going to get sine theta evaluated at 0 and 2 pi. That's going to be 0. And the same thing happens here. I'm going to have this over really 4 in the end. But when I integrate cosine of 2 theta by itself, I'm going to have sine of 2 theta over 2. And the sine of 2 theta, when you evaluate that at 0 or 2 pi, that's going to be 0. Sine of 4 pi is 0, and the sine of 0 is 0. So this and this are just going to contribute 0 to this double integral that we started with, because when we integrate over these, we're just getting something at 0. So we're just left with really the 1 and the 1/2 here. So we have 1 plus a half. So that's 3 halves. And I can take that 3 halves out as a constant. And what I'm integrating then is just 3 halves the integral of d theta, where theta is going from 0 to 2 pi. And this will be 2 pi, just theta evaluated from 0 to 2 pi. That'll give you 2 pi. And so we have then, after canceling a 2, just 3 halves times pi. And that will be our final answer for the area of this region we had in polar coordinates, 3 pi over 2. Fourth question is converting from one coordinate system to another. We have here the spherical coordinates, and we want to know what is the corresponding representation in rectangular coordinates and in cylindrical coordinates. So we want to compute x, y, z, r, and theta is already given to us as pi 6. So really we're after 4 things here. We want to compute x, y, and z, and then we'll have z. We already have theta as pi 6, and we need r still. So let's go ahead. What should we do first? Well, z and r are the things you really should be doing first. They're a little bit easier to compute. Z is rho cosine of phi. Rho is given as 6. Phi is pi 6. And the cosine of pi 6 is square root of 3 over 2. So we're going to have square root of 3 over 2 times 6, or 3 root 3. Again, that's just 6 times the square root of 3 over 2. For r, we're going to have rho sine phi. Sine phi, sine of pi 6 will be 1/2. Rho is 6, so we have 6 times a half, and that'll give us 3. So r equals 3. Once we have r, it's easier to compute x and y, because x and y we can now use their cylindrical coordinates representation. There r times cosine theta and r times sine theta. So I know what r and theta are at this point. R is given here as 3, and theta is pi 6 given in the problem here. So x is going to be r cosine of theta. It's going to be 3 times the cosine of pi 6, which is square root of 3 over 2. So I've just written it 3 times the square root of 3 over 2. Y is r sine theta. R again is 3. And sine of pi 6 is 1/2, so we're just getting 3 halves for y. And let's not forget to answer the question. The x, y, z is going to be 3 root 3 over 2 coming from here, the 3 halves coming from here, and the z was 3 root 3 coming from here. The r theta z, r was 3, theta was given the problem as pi 6, and z again is 3 root 3. So we get that for r theta z. And that gives us the values of this spherical coordinates when you convert them to rectangular coordinates and cylindrical coordinates. Let's turn to a double integral. What should we do here? Let's see, are you going to be able to tell me what to do? Are you going to make me sad or happy here? I'm even wearing my shirt with prime numbers on it. Okay, so what's it going to be? Tell me what to do here. Yes, we want to switch the order of integration. Okay, so that makes me happy. We're happy here. So we want to switch the order of integration, so we want to put a dy dx here, and so we need to know what this region is that we're integrating over so we can switch that order of integration a little bit easier. So let me go ahead and put the region here. Y is between 0 and 6. That's what this is telling us. X is going from y over 3 to 2. X equals y over 3 is the same thing as y equals 3x, and x equals 2. So here is y equals 3x. And notice that when x is 2, y is going to be 6, so we're up here at 2, 6. And since we're interested in x equals 2, it's going to go from here down. And we have that for x equals 2. For y between 0 and 6, and x goes from this line to this line, so we're inside this triangle. X is going from y equals 3x, or x equals y over 3, to x equals 2. So that's the region we're interested in. We want to know what happens to this double integral when we integrate over this region here. And I can switch the order of integration now. Put the dy dx on the outside here, and the dx, x is going from 0 to 2. So I have x going from 0 to 2, and for each fixed x between 0 and 2, we see what happens to y by drawing a vertical line here. Y is going to go from y equals 0, that's the x-axis, to y equals 3x. So from y equals 0 to 3x. So we've switched the order of integration around. We have x between 0 and 2 for each fixed x. Y goes from 0 to 3x. Now we want to integrate this with respect to y. This is just a constant, the square root of x cubed plus 1. So we're just going to get y squared over 2 times that constant when we integrate with respect to y. Y is going from 0 to 3x. This is going to give me a 9x squared over 2. And at 0, we'll just get 0. So I'm going to have a 9 halves times x squared. But I'm going to write that a little bit differently. And instead of writing 9 halves here, I'm keeping a 3 here and then writing 3 halves here. So that's 9 halves x squared again. But keeping the 3 here helps a little bit because you can see that if I take u to be x cubed plus 1, this is just du. The derivative of x cubed is 3x squared. So if I think of u as being x cubed plus 1, I have u to the 1 half du. So I'm integrating u to the 1 half du. That's u to the 3 halves over 3 halves. And u to the 3 halves over 3 halves times 3 halves. The 3 halves will cancel. So we're going to have u to the 1 half du. That's u to the 3 halves over 3 halves times this 3 halves. So the 3 halves cancel. And I just have u to the 3 halves. And since u is x cubed plus 1, that gives me x cubed plus 1 to the 3 halves. And I want to evaluate this from x equals 0 to 2. When I plug in 2, I have 8 plus 1, which is 9, raised to the 3 halves. 9 to the 1 half is 3. So when I cube that, I'm getting 27. I plug in 0, I get 1. So I'm getting 27 minus 1, or 26. So the answer to this double integral we started with is 26. So that's the answer to this question. Now I want to turn to some triple integrals. So here we're just expressing the volume as a triple integral in spherical coordinates. So what is this? This is a sphere of radius square root of 8, or 2 root 2. So there's a sphere of radius 2 root 2 here. Inside we've cut out a cone, and the cone is this cone here. So let's figure out what that cone is in spherical coordinates first. It's z equals the square root of x squared plus y squared, and the way we've been doing this is we first write this in cylindrical coordinates or polar coordinates if you want the x squared plus y squared. Replace it with the r squared. So this is the square root of r squared, or r. So we have z equals r here. Again, it's a little bit easier to work with z and r when we're even in spherical coordinates because these have nice representations, nicer than the x or y. And here z is rho cosine of phi, and r is rho sine phi. So let's write that down. And we can see then by dividing by rho cosine of phi that tangent of phi is 1. And this angle will be pi fourths. Remember, phi has to be between 0 and pi. There's only going to be one phi where in that range where tangent of phi equals 1, and that's phi equals pi fourths. So this cone is the same as phi equals pi fourths. That's another description of this cone. How do we set up this integral in spherical coordinates? Well, the z-axis is going right straight down the middle of this sphere, with the sphere centered at the origin. So the z-axis is going right down the middle of the sphere. We're going all the way around the z-axis for this sphere. So theta is going to go from 0 to 2 pi. The shadow of this will be a circle in the xy plane. Theta is going to go from 0 to 2 pi. Phi is going from this cone. That's the smallest angle. Remember, start at the positive z-axis. We're moving this until we get to the solid. That's when we get to this cone here. That's the first time you hit this solid if you start at the positive z-axis and turn this way. So phi is equal to pi fourths there, and then we go all the way down to the negative z-axis, and there phi is pi. So phi is going from pi fourths to pi, from this cone down to the negative z-axis. And rho is going to go from 0 to the radius of the sphere, which was then 2 root 2. And we're doing volume here, so we're going to integrate rho squared sine phi d rho d phi d theta, since that's dv. So again, theta goes all the way around the positive z-axis from 0 to 2 pi. Phi is going from the cone to the negative z-axis, so from pi fourths to pi. And rho is going from 0, the origin, to the sphere, to root 2. That's the radius of that sphere. This is just dv again, rho squared sine phi d rho d phi d theta. So this gives us the representation in as a triple integral in spherical coordinates for this volume. And again, that's all we wanted to do, was just to write down this triple integral. So that's the answer to this question. Let's go to another triple integral problem. This time we want to calculate the volume, so we want to calculate the integral we end up with. And we have to decide whether we want to use cylindrical or spherical coordinates. We have this picture here. This is elliptic paraboloid, and it starts at the origin and opens upwards, so that's the one on the bottom here. This is also an elliptic paraboloid. It starts at 4 on the z-axis and then opens downward. So that's going to be the top. So we have that solid we're working with. We want to use cylindrical coordinates. What would happen if we were using spherical coordinates? You would start at the origin here for rho, and sometimes you'd be going to this surface, this paraboloid, and sometimes we're going to the other paraboloid. And so rho is not going to look nice if we try to use rho in spherical coordinates. Whereas in cylindrical coordinates, you see we have a circle in the xy plane we're integrating over. At least it looks like that. We'll calculate it in a second. And z is just going from the bottom to the top. So z is going from this, what we'll call 3r squared, since we want to write this in cylindrical coordinates, to the top here, where it's just 4 minus r squared. And again, one hint at what to use is in the actual problem itself. When you see x squared plus y squareds, that's something nice in cylindrical coordinates, just r squared. And that usually is an indication, at least, of maybe wanting to use cylindrical coordinates. So let's set this up. Again, we need to know what this intersection is. Let's make sure it's a circle. We want to know when z equals 3r squared and z equals 4 minus r squared, where they intersect. And we're just going to get 3r squared is equal to 4 minus r squared. And so 4r squared equals 4. Dividing by 4, we see r squared is going to be 1 and r is going to be 1. Again, r is greater than 0. So r is going to be 1. And that tells us that this is just the same as r equals 1. Or if you want, x squared plus y squared equals 1. But it's a circle of radius 1 centered at the origin. And if in the xy plane. So if you imagine the shadow then of this solid, it's going to be a circle of radius 1 centered at the origin in the xy plane. So that means when we set up the integral here, that we're going to get theta going from 0 to 2 pi. Again, we're going all the way around the z-axis here, the circle. So r is going from 0 to 1 because that's the radius of this circle, the shadow we're going to have in the xy plane. And z is going from the bottom to the top. So again, we're going to positive z direction. We hit this first, that's z equals 3r squared. Then we hit this, which is z equals 4 minus r squared. So z is going to go from 3r squared to 4 minus r squared. And we're interested in volume, so the dv is going to be r dz dr d theta. So when we set this up, theta again is going to be 0 to 2 pi in that shadow here of the circle of radius 1 centered at the origin. R goes from 0 to 1 in that shadow. And z goes from the bottom here, where z equals 3r squared, to the top, where z equals 4 minus r squared. And this again is dv, r dz dr d theta. So to calculate this volume, we just want to solve this triple integral here, evaluate it. So when I integrate r, I'm just going to get rz, because r is a constant, and z is evaluated from 3r squared to 4 minus r squared. Notice that 4 minus r squared minus 3r squared is just 4 minus 4r squared. So I have a 4r here. When I integrate that, I'm going to get 2r squared. You're going to get 4 times r squared over 2, which will be just 2r squared. And I have a minus 4r cubed here. And when we integrate that, we get r to the fourth. The derivative of r to the fourth is 4r cubed with a minus sign. So when we integrate this, we should have 2r squared. Again, the derivative of that's 4r. And a minus an r to the fourth, because the derivative of that's going to be minus 4r cubed. We want to evaluate this from 0 to 1. I plug in 1, I get 1. I plug in 0, I get 0. So this is just 1. So we're just integrating d theta, and we're just going to have then 2 pi when we integrate that because it's 1 d theta. So you just have theta evaluated from 0 to 2 pi, or 2 pi. And that's the value then of that triple integral that we started with, that volume. The last problem is the following problem. We just want to calculate this triple integral. It's in x, y, and z in rectangular coordinates. And we can sort of see we probably want to convert this because it's hard to at least integrate with respect to x or y. We could maybe integrate with respect to z if we interchange the order of integration. But we see the x squared plus y squared here, which suggests maybe using cylindrical coordinates because we can replace that with r squared. And we'll get an r dz dr d theta here, and integrating r sine r squared won't be terrible. Let's make sure the solid we have that we're integrating over looks okay for using cylindrical coordinates. So first, we check what's happening in the yz plane. We see z is going between minus 1 and 3, and y is between 0 and the square root of pi. These are both numbers here. The numbers here and numbers here. That means it's a rectangle in the yz plane. You just have z between minus 1 and 3 and y between these two numbers, 0 and the square root of pi. That's just going to be a rectangle. And x is starting at 0. X equals 0 is the yz plane. So you're starting at that rectangle we just described. And it's going to x equals this. What is x equals this? This will be x squared plus y squared equals pi. That's a circle in the xy plane. In space, in 3D, it's going to be a cylinder. We're taking this circle in the xy plane and just going up, straight up and down. So the center of the cylinder is the z-axis. We don't get the whole cylinder because we're just going over this rectangle in the yz plane. The picture looks like this. We have a rectangle in the yz plane, and we're going from that rectangle, where x equals 0, to this cylinder. Now, notice that the length back here, this rectangle, y was the square root of pi here. So this is square root of pi. Y was going from 0 to the square root of pi. And that is the same thing as the radius of the circle we were talking about. X squared plus y squared equals pi. The radius of that would be square root of pi. And so we are just getting that circle then that we want right there. So the shadow of this will be this quarter of a circle in the xy plane. Certainly this is easy to integrate over using cylindrical coordinates, so let's go with it. It's a quarter of a circle. Theta is going from 0 to pi halves. R is going to go from 0 to the square root of pi because the radius of this circle was square root of pi. Z then is just going from the bottom to the top. Z equals minus 1 to 3 is going to stay the same. So theta again goes from 0 to pi halves because we just have this quarter of the circle as a shadow in the xy plane, and you're just going from the positive x-axis to the positive y-axis. R is going from 0 to the square root of pi, and z again is going from minus 1 to 3. This was not a volume. X squared plus y squared is r squared. Here we're integrating sine of r squared. And then we have dv here, r dz dr d theta. So this is the triple integral in cylindrical coordinates that we want to calculate. So let's go ahead and do that. We're integrating with respect to z first, so this is just a constant. And we're going to evaluate z from minus 1 to 3. You can see we just get 3 minus a negative 1 or 4. So this is going to end up being 4 sine of r squared r. Okay, I'm going to write that in a little different way. I'm going to put 2 here and 2r here. So this 2 times 2 is the 4 we got from evaluating z from -1 to 3. And the reason I'm doing that is because if I think of sine u here, this is du. So again, we have sine u du. We know how to integrate that. We're going to get minus the cosine of u. So this will be minus cosine of r squared when I integrate it. So again, we have sine u du here. Minus cosine of u will be the integral of that. So we have minus cosine of r squared, where r is going from 0 to the square root of pi. Plugging in the square root of pi, we have cosine of pi, which is -1. With this minus sign, this becomes a +1. Then we want to subtract -1. Cosine of 0 is 1. So subtracting a -1, so we're adding 1 to the 1 we got when we plugged in square root of pi. And so this is going to be 2. So we're getting 2 for this. So now we're going to have 4 times the integral from 0 to pi halves d theta. And of course, this part's just going to be pi halves. You're just going to get theta evaluated from 0 to pi halves. So you get pi halves times 4, which is 2 pi. So the answer to this problem, like the last problem, is 2 pi. So that finishes this lecture. We finished these 8 problems that were on this old test 3, and I'll finish there.